This video will cover an introduction to data transformations for data analysis in further mathematics. So firstly, let's think about why would we need a data transformation. So up to this point, we are looking at bivariate numerical data. So we're looking at two sets of numerical variables and comparing them by using scatter plots. We have investigated whether there's an association. We have potentially looked at applying a linear model, a least squares regression line. But perhaps we've noticed throughout our regression analysis that our data is actually non-linear. So that doesn't mean we stop. In further mathematics, what we do, even though we only look at linear models, so a least squares regression line, we can potentially transform our data. So that is, we apply a particular model or rule to one particular set of the data, so one of the variables, so that we are effectively manipulating it, but we're doing it in a consistent way. So it's not like scaling. If you think of scaling in VCE, how VCAA scale our study scores, it's a similar type of thing. We're applying a rule to one of the pieces of data or one of the variables, and that will enable us to linearize our data. So what that means is we take something that is nonlinear, curved, and we have the ability to either stretch out or compress in one of the scales of one of the variables to have the effect of realigning. So the example I've got here, we can see we've got some data in this first scatter plot, and if we look at the general shape, we can see it's got sort of that curved exponential type form. And it's really hard to see down the bottom here, but if you look at the x-axis scale, so here it's going up 1, 2, 3, 4, 5, 6, but then here we can see our numbers are actually going up by 5, so 5, 10, 15. So what has happened, we've actually applied what we call a squared transformation to our x-axis or our EV. And what that has had the effect of doing is stretching out these variables, so stretching them, and our data is a bit more in line. Now, I would say this has still probably got a slight curve to it, but it's far less pronounced than before. So by linearizing our data, trying to make it more linear, by stretching out our x-axis variable, we've got data that now is of a more linear form. Therefore, it's appropriate to go ahead and apply a least squares regression model to that set of data. Okay, so we've decided that we need to transform our data. And I'd mentioned in the previous slide that we were applying a squared transformation. We have 3 different transformations that we are able to apply. A squared transformation, and as I said, that has the effect of whichever variable it is stretching out that data. We have a log transformation, very similar to what we did in univariate data with log histograms, where if I apply a log transformation, what that will actually do to my data is compress the scale. So it will take very, very large and spread out numbers and compress them down to a much smaller range and smaller values. And finally, we have what we call a reciprocal transformation. So a reciprocal is if I've got the number 2, the reciprocal of that becomes 1 over 2. So the reciprocal is taking, I guess, that fraction and turning it upside down. You may have heard of that word before when you're looking at parallel gradients in linear equations and graphing. So it may be a term that you're familiar with. If not, we need to know that that is talking about taking a y variable and making it 1 over y, or x and making it 1 over x. So all 3 of these types of transformations can be applied to either the explanatory variable, your x-axis, or the response variable, your y-axis. We only apply it to one of them. We don't do 2 at a time, so we only ever apply one transformation to our set of data. And when we go on to actually represent that transformation, we do that in terms of writing our variable as that transformed version. And we'll talk more about that as we do some examples. Okay, so I think I need to do a transformation. My data appears nonlinear. How do I know what I can do? And so here we have what we call the circle of transformations, a really, really, really important piece of information to have in your BAM reference. So this diagram here is just a different version to the diagram that's in your notes. And you'll note the circle works by taking, if you take a particular component, so if I take just this section here, the first quadrant, what it means is that if I have a scatter plot that has that general shape, okay, it's curving and it's starting at the top, it's like that top quarter of the circle, that top right hand side. What this diagram is telling me is that an x squared or a y squared transformation would be appropriate. So remember, a squared transformation has the effect of stretching the axis. So an x squared would take these values and stretch them out so it become more linear, okay? Similarly, if I have something in this third quadrant here, so a graph, a scatter plot, when I look at it, that is kind of this shape, so it's curving on the lower left-hand side, then I have 4 possible transformations. I could do a log x, which will drag my x values back in, or a log y, which will bring down my y values and compress that axis. Or I can do a reciprocal of either the x-axis or the y-axis. And we'll talk a little bit more about what a reciprocal transformation also does in one of the examples. Okay, so a couple of quick examples about how we would apply it. And this is the type of question you could be asked in the exam. Often you're given a scatter plot and you're asked to identify what might be an appropriate transformation. So what we want to do, if we take this first scatter plot here, we want to think about, well, what's the general shape of the data? And I can see it is kind of curved and it's arcing this way. So that would match with my first quadrant of my transformation circle. And so the possible transformations that I could do here in this situation are either an x squared or a y squared. They will give me the best result possible. In the second example, again, we're looking at the general shape, and here we can see we're curving up in that exponential sort of shape. And so that's my fourth quadrant here. And so looking at the options I have there, I could do an x squared or a log y, or even I could do a 1 over y, a reciprocal of y. With the reciprocal of y, I will note now that whenever we are applying a reciprocal transformation, what that will do, it'll make very big numbers very, very small, but it'll have less of an impact on the smaller numbers. So if you think about the maximum here of 900, if I was to apply a reciprocal transformation, that would become 1 over 900. So quite a small decimal number. Compared to my lowest value of 100 on the scale. I know the data goes lower than that, but this is just for comparison. If I was to apply that transformation, it would become 1 over 100. So still quite a small decimal value, but bigger, in fact, than the 1 on 900. So what ends up happening with our data is that it actually changes the direction. So all of our y-axis data gets flipped. And so we'll have a look at an example and I'll show you what that looks like when we apply that. But a reciprocal will always change the direction of your relationship. So that's something to keep an eye out for. Okay, we have 2 further examples here. So our third scatter plot, again, we're looking for what's the general shape, and we can see we've got that curve, which is a lot like our third quadrant in our diagram. And so we have the option of a log on either the x or the y axis, or a reciprocal transformation on either the x or y axis. And finally, the fourth one here, we have curving up, so much like the second quadrant, where our options are y squared, log of y, or 1 on x. Sorry, that should be a log of x and a 1 on x, reciprocal of x. So at this point, you might be thinking, that's great, but what happens if there are 3 or 4 options to transform my data? How do I know what is best? So we're going to have a look at some examples now and look at not only how we perform the transformation using our calculator, but how would we identify what's the best option to move forward with. Okay, so our first example, we're given a scatter plot and a set of data in a table. The question's asking us to use our calculator to apply an appropriate transformation to the data set. So first step is to check what might be a possibility. So looking at our scatter plot, we can see we've got that general curved shape, like our fourth quadrant, that bottom right-hand side of your circular transformations. And so possible transformations are a log y, a 1 over y, or a reciprocal of y, or an x squared. So I've got 3 options. What we're going to do, this will help us practice, do each of the transformations in our calculator, but then we'll also talk about how we identify which is the best one to move forward with. Okay, so I've gone ahead and put the data in my calculator. I have labelled both of the columns. Remember, it is better to use more than one letter. So I've just called it XX and YY. So the first thing I'm going to do is have a look at the scatter plot of the original data. So going into a data and stats, let's put in our EV and our RV, and we should get a picture very much the same as what we have in our notes. Okay, so we obviously want to transform this and make it more linear. We know that a log y will have the effect of compressing our y-axis and bringing that back into line, those larger points at the end back into line. An x squared will have the effect of bringing in or stretching, the x-axis, so it'll stretch these points out and bring them down into line. And a reciprocal will do a bit of both and change the direction. So let's have a look at what each impact has. So if I wanted to do a transformation in my calculator, I'm going to get the calculator to do the work for me, much like I know how to do from the log histogram stuff that we covered in univariate data. So here I'm going to just put in some labels. So I'm going to call this one Ly for log of y. I'm going to call the next one the reciprocal of y. And finally, my x squared. So I'm actually going to get the calculator to do all the calculations now, and then I'm going to jump to the scatter plot and see what happens. So sometimes you will do a visual check only. Sometimes you will be directed which transformation to do. Sometimes you'll need to do more than a visual check, and we'll have a look at that in a little bit of time. But first, I want to do my transformation. So in this column here, column C, I want to have the log of these y values. So remember, we go to this little grey box. If I put in equals log and then my label for my y values, if I press enter, you will get those values there. Now, at the moment, my calculator is in exact mode. So if you don't like that, what you can do is just quickly go into your settings. So go back to your home screen, into your settings, document setup. We actually want our calculator always on float, and then our calculation mode on approximate. So if I go back into my current, now I've got them in decimals, okay? And it won't round off to a particular number for me. So you can see all of these larger numbers, 98, 12, there's not a lot of difference anymore. They've all become 1 point something, okay? Then when we get to our 3-digit numbers, they're 2 point something. All right, so those numbers have gone from being very spread out to very compressed. So what's the impact of that? I have altered my RV. So what I'm going to do is change my RV axis to this log y set of data. We can watch what happens. So there's the original at the moment, and then now there's my log y. So we can see those data values sort of in the middle where it was curving have been pulled up, have the effect of being pulling up there. What's actually happened is the y-axis has been compressed down. So we have some pretty linear data right there. Let's see though what happens when we check the other transformation. So I'll go back to the original, and now I want to see what happens with the reciprocal of y. So a reciprocal of y is, again, equals 1 divided by your RV, y set of data. And again, I've now got lots of decimals, so you can see really, really quite small numbers coming up there. All right, the bigger the original values are, the smaller the reciprocal values become. So again, let's see what impact that had. I want to change my y-axis, my RV, to the reciprocal transform data. So again, I've got the original sitting here, and then I see what happened. So you can see we changed direction. We moved from a positive direction scatter plot to a negative direction scatter plot. But the impact for the linearization hasn't been as strong as before. We can still see it's quite curved, that data. So at the moment, I would say reciprocal is not an appropriate transformation for this particular data set, even though it is one of the options. And so let's just change that back to the original data. And then we'll go back and try our final one. So we're moving across now to an x squared. So this time, I'm going to square my EV, my x-axis variables. And squared, and again, hit enter. And so we can see now the x values have all been squared. If I check the impact in my scatter plot, this time it's the EV that I'm changing. So my RV, the y-axis, remains as the original data. And this time it's my x-axis, my EV, that has been transformed to that x squared data. So if we have a look at the impact there, so again, we are seeing that that x-axis scale has been dragged out, it's been stretched, and our data has been brought into line a bit more. Now, it's not perfect. I would say that it's definitely an improvement on the reciprocal, but probably not as good as the log y transformation. If we need to be sure, some things that we should check are the R value to see if it has improved and the residual plot. So we can go ahead and check both of those if we were doing a larger question, particularly in our SAC. We'll have a look at that in a different video later on when we're doing some review. But for now, let's go back and apply our log y transformation. And so I'm going to go back, revert to my original x data for the EV, and go back to my log of y for my RV. The question wanted me to pick a transformation and find the regression equation, the appropriate regression equation. So let's pop our regression line on from here. That's the easiest way for us to do it. And we get our regression equation there. Actually, we didn't need to find the regression equation. We just needed to identify the best transformation. So in this case, we said our log of y was our best transformation. So example 2 is a modified version of a VCAA paper question. So this gives you a good indication of what you're generally asked in a SAC type question or again in exam 2. So the number of hours spent doing homework each week and the number of hours spent watching television each week were recorded for a group of 20 Year 12 students. The results are displayed below. So we can see there we've got our scatter plot and our raw data as well. The relationship is clearly nonlinear. Apply a reciprocal transformation to the TV variable and determine the least squares regression equation for the transformed data, giving your equation in terms of the variables and correct to 3 significant figures. Okay, so we are applying a reciprocal transformation to the TV. so to our TV hours. And remembering we want our equation in terms of the variables to 3 significant figures. So very similar to what we've done previously with our linear graphs. So let's put this data into our calculator, apply that reciprocal transformation, and get our new equation for that. Okay, so again, I've gone ahead and put that data in, giving my columns TV and homework. We want to then apply that reciprocal transformation to the TV data. Okay, remember your reciprocal means 1 over the variable, so the TV data there, and I get my values. Let's have a look at the scatter plot. So when I look at my original scatter plot, now I have taken exactly what they showed me in the diagram, where they had TV as the explanatory variable, homework as the response, and you need to, if they weren't given to you, that information, you need to decide which is the explanatory variable, which is the response variable. In this case, given to us, so we replicate that here. Now we want to alter our EV to our reciprocal TV data. Remember, a reciprocal will change the direction, so don't panic when it flips. And we can see there we now have, whilst it's not a nice, straight, perfect, strong line, it is a far more linear set of data. Okay, so now we can go ahead and apply our regression equation. So I'm just going to do it from the graph page since we're here. My regression equation, and I have y equals 5.12 plus 102.9 times x. So be very careful when you're reading these. It might be worth noting down a few decimal places and then rounding to the significant figures that are being asked for. So we'll do that now. Okay, so I've just noted down my value for the y-intercept and slope. Now I need to put my answer in terms of the variables. So we want homework equals, or homework hours equals, our value of A to 3 significant figures, so 5.12, plus B to 3 significant figures, so that will become 103, times, now we need to write the TV hours as the reciprocal. So what that actually means is that we are writing it as 1 over TV hours. So we literally write that here. So 1 over TV hours. And so I've written my equation in terms of the variables and given that to 3 significant figures. So now moving on to some past VCAA questions. First one from the 2018 paper 1, question 11. Freya uses the following data to generate the scatter plot below. The scatter plot shows that the data is non-linear. To linearize the data, Freya applies a reciprocal transformation to the y variable. She then fits a least squares line to the transformed data. With x as the explanatory variable, the equation of the least squares line is closest to. And we've got our options there. So before we go ahead and put this data into our calculator, we want to check, can we eliminate any of the options? And so firstly, noting that we are applying the reciprocal transformation to the y variable means that our final answer needs to be written in the form 1 over y equals a plus bx. So firstly, we can say, well, D and E are not appropriate answers. The second thing to note is that with a reciprocal transformation, the direction of our scatter plot will change. So at the moment, whilst it's non-linear, it's still in a negative direction, which will mean our transformed data will change to a positive direction, meaning B is a positive value. So when we look at the options here, we can see A, we have a positive slope, B has a positive slope, but C has a negative slope. So again, C is not an appropriate answer. Sometimes you'll get the situation where you're only left with one potential answer there. But in this case, we have 2. So now we need to enter the data into our calculator, apply the reciprocal transformation to the RV, and find the new equation of that least squares regression line. So coming across to our calculator now, I've put in the EV, the X variables, and the RV. And we wanted to do a reciprocal of the Y values, or the RV. So I'm going to ask my calculator to do that. So 1 divided by my RV values, and I get my new data for the RV there. This time I'm not going to check the scatter plot. I'm just going to go ahead and find my regression equation from within the Listen Spreadsheets page, so the alternative way. So remember to do that. We're going into Menu, Statistics, Stat Calculations, and number 4, Linear Regression. We tell our calculator that we have our XList is our EV, so still the original XList data, but our Y list will be our reciprocal of Y, our transformed data. Click OK, and here we get our values. So both quite small values, negative 0.0039, and for the slope, 0.01179. Okay, so then from that, we can see when we go back to our options, that option A is going to be our best answer. And so here, option A. Our next example is from the 2016 paper 1, again, question 11. The table below gives the Human Development Index, the HDI, and the mean number of children per woman, given as children, for 14 countries in 2007. A scatter plot of the data is shown. So you can see we've got our original data, we've got our scatter plot here. It's important to take note that the HDI, the Human Development Index, is our explanatory variable there, and the number of children per woman is our response variable. So the scatter plot is non-linear. A log transformation is applied to the variable children to linearize the scatter plot. With HDI as the explanatory variable, the equation of the least squares line fitted to the linearized data is closest to. So very much like the previous example, firstly we want to think about what form should our answer take. So with a log transformation being applied to children, that means our answer is going to be written as log children equals A plus B X, or really B times HDI. So from our options there, we can then eliminate option B and option D as not appropriate. The second thing we can look at is the direction. Okay, so again, we have a negative direction there with our original data, which means we would have a negative slope. A log transformation, we keep the same direction, so it actually means here in our equation it's going to be minus B. And so looking at the options left, we can actually see that all three, A, C and E, all have a negative slope. So in this case, that's not helpful. Another thing that we might be able to use to help us eliminate some options is if we understand and remember that a log transformation will actually compress this axis here, the response variable. So it will make the larger numbers smaller. So our maximum is not going to be above 8. That might give us a hint about what our y-intercept would be. So it's unlikely we're going to have a y-intercept of 21, like in option E. It's unlikely we're going to have a y-intercept of 8, like in option C. It's more likely that we're going to have a y-intercept of 1.1. So I think at this stage that A is our best answer. But obviously in an exam, we don't want to think we're right, we want to know we're right. And so what we need to do now is enter that data into our calculator, perform the transformation, so log of the children data, and find our new least squares regression line. Okay, so I now have that data entered. I'm going to do my log of the children data. And so asking my calculator to do log of children, getting my values there, and again, finding the regression equation. So the time-consuming part of this is actually the data entry, not the calculation of the regression line. So once we have that in, so we're going our HDI as our X list, our log children as our Y list, and then we can see our value of A here, 1.058 or 1.01, our value of B, negative 0.0097. And so looking back at our options, that confirms that A is our best option. And so here, 1.1, negative 0.0095, confirming A. Final VCAA question. So this is the 2017 paper 2 this time, question 4. So here we have some data. This association between the area of a forest eaten by the caterpillars and the year is non-linear. A log base 10 transformation is applied to the variable area. So we're applying to our area here to linearize the data. Perform the log transformation to the variable area and determine the equation of the least squares line that can be used to predict area from year. So there they're giving you a hint of what is the EV and what is the RV. Write the values of the intercept and slope of the least squares line in the appropriate boxes provided below. Round your answers to 3 significant figures. Okay, so this time we don't have a scatter plot to help give us a hint, and we may not understand what they mean by predicting here, but we can see they've given us the form of the equation. So we can see the EV is year and the RV is area. That's just reconfirming what we would already understand, making sure we're getting things the right way around. Okay, what we need to do again is put this data into our calculator, apply that transformation, and then find our new regression equation. Okay, so here I have the data sitting ready to go. We are going to find the log of the area as our transformation. So again, asking my calculator to find the log of the area variable, getting my values here. I'll draw the scatter plot this time. So we have year as our EV and the log of the area as my RV. You can see we've got a fairly nice linear relationship now. And let's apply our regression equation. Going in, making sure we're doing it in that form A plus BX. And here we have our equation. So we're told our y-intercept, negative 14.4, and our slope at 0.0085. So we're now just going to transfer that to the spaces provided in the question. Okay, so when I'm doing a question like this, I often write down the unrounded or a longer version of the variables and then put my final answer in the box. So I would suggest if you are going to do that, do it above the box so that the final answer you're giving is in those answer spaces, and rounding to 3 significant figures. So for our y-intercept, we've got negative 14.4. And for our slope, we've got 0.00854. Remember, you start where that first non-zero digit is and look to the 4th one to tell you whether you need to round for 3 or not. In this case, we do. Okay, so that's it for transformations. Hopefully that was helpful.